Hello, everybody. This is Bert Dixon here presenting tonight on the arc length and area of polar curves. Before we get into that lesson, I'd like you to explore one of the topics that we talked about last week or in the last lecture. We graphed a four-petaled rose last week, and we found that it started. Let's see. Started like this, and it went to here, and then to here, and then to here, and so on, and created a four-petaled rose like that. And so that was when we had we graphed cosine of 2 theta. R equals cosine of 2 theta was that graph. And so we had when n was 2, or when m was 2, we got 4 petals. So what I'd like you to do is go ahead and graph the same thing with m equals 3, then m equals 4, then m equals 5, m equals 6, m equals 7. So for example, you're going to have r equals cosine of 3 theta, and then r equals cosine of 4 theta, and so on and so on. And see if you can recognize a pattern between how many petals there are and what m is. So go ahead and pause your video and try producing a few of those graphs, and press play when you're ready. So if we set up a table with m and the number of petals, when m is 2, that was the one we did in the last set of notes, we have 4 petals, and then we can go to m equals 3, and so if I graph, let's turn this one off, and graph this one. So when m is 3, we have 3 petals. And then if I graph with m equals 4, we have 8 petals. When m is 5, we get 5 petals. And so what you'll notice if you keep going and do also 6 and 7, you'll recognize that when m is even, like 2 and 4, the number of petals is twice m. So if m is even, the number of petals is 2m. When m is odd, the number of petals is just m. That's 3. If m is 3, we get 3 petals. If m is 5, we get 5 petals, and so on. Okay, so and that will work for sine as well. So if you graphed something like y equals, or not y equals, but r equals cosine of 6m, sorry, sine of 6m, that would have 12 petals. So the same pattern exists for sine as it does for cosine. Okay, so the new material for this lesson, when we're finding the area between the pole and any polar curve, r equals f of theta, from a starting angle to alpha to an ending angle beta, then this integral will find the area for us. And so what we need to understand is that if we have a polar graph, let's say it looks like this, and we start at some starting angle, which is alpha radians, and it ends here at some angle beta. What's happening is the area that we're calculating is not the area under the curve like it was when we were in Cartesian. When we are talking about the area inside a polar curve, what we're really talking about is the area that is swept out by all the radii. So if you have the starting radius here, and if we keep sweeping the radii out, so every time I increase the angle a little bit, it moves along the curve. So the ending of the radius moves along the curve. So all these radii are going to have different lengths, but what we're doing is we're calculating the area from the pole, which is the origin, to the curve. And so that is the area that gets swept out by those radii. And if you notice that what I drew when I was sweeping out those radii, I was really just drawing a whole bunch of sectors. So this is like a sector, not to a circle, but to a curve. So you might remember maybe in high school geometry how to find the area of a sector. In degrees, the way we find the area of a sector is the number of degrees over 360 times pi r squared. And then if we do the same thing in radians, that would be the number of radians, which we could call theta, over 2 pi times pi r squared. And so notice the pi's cancel, and that just ends up being 1/2 r squared theta. So the area of a sector is 1/2 r squared theta, and that's why in the integral it's 1/2 r squared d theta, because if you imagine each one of these sectors that I'm drawing over here has an infinitesimal change in angle, which we would call d theta. So we're drawing a skinny little sector like this with an angle of d theta. And so if we add up all of those possible sectors, that's what the integral does. Remember, the integral is just taking a sum of a bunch of quantities, and it's the sum of all of those sectors in this case, analogous to when we did it in Cartesian. When we found the area under a curve, it was finding the areas of a bunch of rectangles with an infinitesimal base width of dx. So now our infinitesimal piece is our angle d theta. So that's where this formula comes from, 1/2 r squared d theta. And so for example 1, we're going to find the area inside this cardioid. So first let's draw a sketch. And so the graph of the cardioid, if we plug in 0 radians for cosine, cosine of 0 is 1, so we get 1 plus 1 is 2, times 2 is 4. So it's going to start out here at 4, and then at, let's say, pi over 6, cosine of pi over 6 is 1/2, so we'd have 3/2 times 2 is 3. So if we're at, I think I said pi over 6, but I meant pi over 3, so that would be 60 degrees or pi over 3. So if we're at pi over 3, that's going to be 3 units away. So 1, 2, 3 units away, so maybe right about there. Okay, and then if we plug in pi over 2, cosine of pi over 2 is 0, so 2 times 1 plus 0 is 2, and so that puts us here. And then at pi, cosine is -1, or we could even go, let's do another intermediate angle here, so 2 pi over 3, cosine is -1/2, so then we're going to get 1 And then at pi, cosine of pi is 0. Or sorry, cosine of pi is -1. So we have 1 plus -1 is 0 times 2. 2 times 0 is 0. So our radius is 0 when we're at an angle of pi. And so if we trace out those points that we just plotted, we get this cardioid. And then if we keep going, it's just going to give us the same thing down here. And so there's our cardioid. And try to make it look somewhat symmetric. Not doing a very good job of that. And so now if we wanted the area inside this cardioid, remember it's going to be, the area is going to be swept out by a bunch of radii. And so our first radius is this one right here at 0. Let's just find the area of half the cardioid, and then we will double it. And so if I start at 0 and I just start sweeping out radii from the pole to the curve, okay, we're adding up all of these sectors. And so that's going to end when I'm at pi, and that'll fill in half of our cardioid, and then we'll just double it. Okay, so the area of the cardioid is going to be 2 times the integral from 0 to pi of 1/2 r squared. Now r is 2 times 1 plus cosine theta squared d theta. And so that is 2 times the integral 1/2 0 to pi, and then that's, if I square the if I square r, then that ends up being 4 times 1 plus 2 cosine theta plus cosine squared theta d theta. And so 1/2 of 4 is 2, and then we have a 2 outside, so that's going to be 4 outside. And then the integral from 0 to theta of 1 plus 2 cosine theta. And then let's see, cosine squared we can write as 1 plus 2 cosine theta over 2. Or no, 1 plus cosine of 2 theta over 2 d theta. And that way we can find the antiderivative. So I just replaced the cosine squared with 1 plus cosine 2 theta over 2. And so our antiderivative is theta plus 2 sine theta plus 1/2 theta from here. And then this is going to be sine of 2 theta over 4. From 0 to pi. And so that is pi plus sine of pi is 0 plus 1/2 pi plus sine of 2 pi is 0. When I plug in 0, all of them become 0. And so that ends up being 4 times 3/2 pi is 6 pi. And with this one, it also would have worked out just fine if we would have done the whole thing. We could have integrated from 0 to 2 pi, 1/2 r squared d theta, and that would have worked out to be exactly the same answer. Okay, for the next example, this time we're finding the area inside the same cardioid that we just worked with, but outside of the circle r equals 3. And so this gets a little more complicated when we work with multiple curves. And so we already know what our cardioid looks like. So our cardioid looks like that. This is 4 units out here. And then the circle, r equals 3, would be, so that's 2, 3 would be about like that. And 1, 2, 3. So the circle r equals 3 looks like this. And we're looking for the area that's inside the cardioid, but outside of the circle. So we're talking about this area right here. Okay, and so the way that we're going to have to do that, remember, when you do an integral of a polar curve, it's giving you the area that's traced out by the radii. So if we start drawing radii here from the pole to try to fill in that blue highlighted area, we're going to get a lot more area than what we really want. So this is where we're going to start, but then we have to subtract off the area that we don't want, which is the yellow area here. And so and that'll give us the blue area. So it's going to look like this. And we're just going to work with half of it again and then double. So this area that we're trying to find is equal to this area minus the yellow area. Okay, and so to get the blue area, we're going to do the integral from 0 until these curves intersect. So that's a good question. Where do they intersect? At what angle is that where they intersect? And so if we set the two curves equal to each other, 2 times 1 plus cosine of theta, when does that equal 3? So if I divide by 2, I get 1 plus cosine theta equals 3 halves. Subtract 1, we get cosine theta equals 1/2. And so that point where they intersect must be at pi over 3, because that's the only time that cosine is equal to 1/2 in the first quadrant. And so we're going to go to pi over 3 and 1/2 r squared. So this curve along here is the cardioid. And so that's going to be 1/2 of 2 times 1 plus cosine of theta squared d theta. And then we're going to subtract the yellow area. Now the yellow area is just a normal sector inside a circle. So we don't have to use calculus to do that, but we can. We can write an integral from 0 to pi over 3, 1/2 r squared. In this case, our radius is 3, so 1/2 of 3 squared d theta. But just keep in mind that we could also get that area just by doing area of a sector of a circle. Since it's pi over 3, that's 60 degrees, and that's 1/6 of a circle. So that should be 1/6 of pi times 3 squared. And so that's 9 pi over 6, or 3 pi over 2. So we should get that same answer when we evaluate this integral. We should get 3 pi over 2 as well. So let's go ahead and work this out. So the first one is, this looks very much like the integral that we had in the previous problem, except the endpoints are different. And so we have, when we square the 2, that becomes 4. Half of 4 is 2. So we're going to have 2 times the integral of 1 plus 2 cosine theta plus cosine squared theta d theta. And that is theta plus 2 sine theta plus 1/2 plus cosine of 2 theta. Actually, that's what this is equal to. This is equal to 1/2 plus cosine of 2 theta. So when we take the antiderivative, that's going to give us 1/2 theta plus sine of 2 theta over 4 from 0 to pi over 3. This integral is becomes the integral from 0 to pi over 3 of 9/2 d theta. So that becomes minus 9/2 theta from 0 to pi over 3. Okay, and so when we plug in pi over 3 into this integral, we end up with pi over 3. Sine of pi over 3 is root 3 over 2 times 2 is just root 3. And then we'd have pi over 6. And then sine of 2 pi over 3 is also root 3 over 2. If we divide by 4, then we get root 3 over 8. And when we plug in 0, they all become 0. This becomes minus 9/2 times pi over 3. And so now if I distribute this 2, we have, actually before I distribute that, I'm going to put these together. So that's going to be pi over 2 when you put those together, times 2 is just pi. And then if we put these together, we get 9 root 3 over 8 times 2 becomes 9 root 3 over 4. And then this is minus, this is 9 pi over 6, which is 3 pi over 2. And so now we have 9 root 3 over 4 minus pi over 2 when we put these two together. And that is only for this area. And remember, we need to double that. So the total shaded area, which is this, is going to equal twice that. So 2 times 9 root 3 over 4 minus pi over 2 becomes 9 root 3 over 2 minus pi. And so that is our total area of this light blue region up here, outside of the cardioid, but inside, or sorry, outside of the circle, but inside the cardioid. Okay, I would like you to try example 3. you're going to find the total area inside the rows. Now remember, this is an odd value, so that means it's going to have 3 petals. So this rose has 3 petals. What I suggest you do is just find the area of 1 petal and multiply by 3, or you could even find the area of half a petal and multiply by 6. So especially with these rose patterns, you want to work with the smallest area possible and then just multiply by however many there are. You don't want to just blindly integrate from 0 to 2 pi, because a lot of these rose patterns trace over themselves multiple times if you go from 0 to 2 pi. So give this one a try, see if you can find the area of just 1 petal or a half a petal, and then use that to find the area inside the entire rose. Okay, so this is a 3-petaled rose. Now cosine graphs always start out here. So in other words, when we plug in 0 for theta, in this case we get cosine of 0 is 1 times 4 is 4. So this is going to start off out here 4 units away, and then it's going to come back to the pole, and we need to figure out how what angle brings us back to the pole again. So we want to know, when is 4 cosine of 3 theta going to equal 0? And cosine is equal to 0 whenever this angle inside is equal to pi over 2 for the first time. So 3 theta, when is 3 theta equal to pi over 2? That's when theta is pi over 6. And so it's an angle of pi over 6 that gets us back to the pole, and that creates the half petal. Now, even though this rose is a total of 3 petals, it's going to be something like that. We're just going to focus on this half petal that I've shaded in right here, and then multiply by 6. And so the area of the half petal is equal to the integral from 0 to pi over 6, 1/2 r squared d theta. And so that's 0 to pi over 6, 1/2 of 16 cosine squared 3 theta d theta, and that is 8 integral from 0 to pi over 6, and then the cosine squared we can write as 1/2 plus, this would be cosine of 6 theta over 2 d theta. And so we're just using the identity. That would be 1 plus cosine 6 theta over 2, because it's a double angle. And if it started with pi over 3, when we double it, or sorry, not pi over 3, but 3 theta, when we double it, it becomes 6 theta. And so then now we have an integral that we can evaluate. So that's 8 times 1/2 theta plus sine of 6 theta over 12 from 0 to pi over 6. And so that is, when we distribute, we'll leave the 8 out here for now. So then we have 1/2 of pi over 6 plus sine of pi, which is 0. And then when we plug in 0, we also get 0. So minus 0 minus 0. And so we just end up with 8 pi over 12, which is 2 pi over 3. And then if we multiply that times 6, so the area inside the entire rows is 6 times 2 pi over 3, which is 4 pi. So now we're going to take a look at finding the arc length of polar curves. So just to review some arc length equations that we've worked with already. Early on in the course, we learned that the length of a curve is just the square root of 1 plus dy dx squared dx. And then in parametric, we learned that we'll just integrate from one starting t-value to an ending t-value, and it was the square root of dx dt squared plus dy dt squared dt. And so now we have a similar formula for arc length using polar curves. So it's r squared plus dr d theta squared d theta. And most of these expressions are going to be pretty difficult to integrate by hand, so we will use a calculator some of the time, depending on what our functions are. And so for this one, for example 4, we'll use a calculator to find the perimeter of this figure, which looks like a infinity symbol. It's called a lemniscate. And so it's going to be, let's just do one part of this curve, and then we'll multiply by 4. So if I go from here until it touches the pole the first time, we're going to multiply that by 4. So the arc length equals 4 times the integral from 0 until it reaches the pole for the first time. That's when 2 theta is equal to pi over 2, because cosine of pi over 2 is 0. And so that's theta equals pi over 4. So it's going to be pi over 4 when it reaches the pole for the first time. And so we're just going to do 4 of these red curves. So if I find the area, or sorry, find the arc length of that, I'm just going to multiply by 4. And so we already have that 4 out in front. And so now it's the square root of r squared, which is 4 cosine of 2 theta, plus dr d theta. And so if we take this equation over here, we would get, if we take the derivative, we would get 2r dr d theta equals negative 8 sine of 2 theta. And so dr d theta equals negative 8 sine of 2 theta over 2r. And that is negative 8 sine of 2 theta over 2 times the square root of 4 cosine 2 theta. So then if we square that, that's going to be 64 sine squared 2 theta over 4 times 4 cosine 2 theta. So that ends up being 0 to pi over 4, 4 cosine 2 theta plus 16 sine squared 2 theta over cosine. Sorry, actually this would be 4. It's 64 divided by 16 is 4. Sine squared 2 theta over cosine of 2 theta d theta. Okay, so you can now use a calculator to evaluate that integral. Four times math 9. That gives me an integral from 0 to pi over 4 and then we have the square root of 4 cosine 2 theta plus 4 sine of 2 theta squared divided by cosine 2 theta And so we get 10.488. The approximate value of that integral. So that's the approximate arc length of the entire lemniscate because we already multiplied by 4 of them. So there's another one here, and another one here, and another one here. So again, same suggestion I gave with the rose patterns. Anytime you're not sure how many times a curve is going to trace over itself, just do one simple part of the curve and then multiply by, in this case, we multiplied by 4 to get the total arc length. Okay, so now I would like you to pause your video and try example 5. Use the arc length formula to find the perimeter of this cardioid. So since r equals 1 minus cosine 2, or 1 minus cosine theta, r squared would be 1 minus 2 cosine theta plus cosine squared theta, and dr d theta would be positive sine theta. And so now this cardioid, by the way, if we plug in 0 for theta, we get 1. So 1 minus 1 is 0. And then if we plug in pi over 2, we get 1. If we plug in 2 pi, we get, or sorry, plug in pi and you get negative 1. So then we have 1 minus negative 1, which is 2. And so that looks like this. And then we'll just keep going to get the other half of it. And so there's our cardioid. And so we can get the arc length for this one. It is one continuous curve. Cardioids only trace over themselves once. For example, we went from 0 to pi, and that gave us half of the cardioid. So if we do pi to 2 pi, that would give us the other half. So we can just do this one all in one shot. The arc length is equal to 0 to 2 pi square root of r squared. R squared we have up here is 1 minus 2 cosine theta plus cosine squared theta. And then we have dr d theta squared, so that's going to be sine squared theta. And this one we can actually integrate by hand. You could use a graphing calculator, or like I said, this one can be done by hand, because when you simplify the entire inside, cosine squared plus sine squared is 1. And so then we end up with, after a few simplification steps, we end up with just the integral of 2 minus 2 cosine theta d theta, and then that is 4 4 sine squared of theta over 2 using a double angle identity, and then we end up with integral from 0 to 2 pi of 2 sine theta over 2 d theta, and that is negative 2 cosine theta over 2 divided by 1/2. It's the antiderivative from 0 to 2 pi gives us 4 minus negative 4, which is 8. So the total perimeter of this cardioid is 8 units. If you had typed it all in your calculator from this first step, you should get the same answer. You should get 8 on your calculator. So that completes all of the examples for section 11.5. And here are some suggested problems for you to practice on before you try the online assignment. Let me know if you need any help. Have a great day.